Good day, everyone, and welcome to the webcast series, Mainstream Wastewater Nitrogen Removal using Partial Denitrification Anammox, or PdNA. You'll be hearing that acronym a lot today. My name is Jeff Moeller, and I'm the Director of Research Services at the Water Research Foundation. And I'll be serving as the moderator for today's webcast. This webcast is part 2 of a 2-part webcast series on PdNA. Part 1 of the webcast series focused on providing an overview of PdNA and also assessments that utilities can use to determine if PdNA is a right fit for them. But no worries if you were not able to attend part 1. Part 1 is by no means a prerequisite for part 2 here. It just provided some useful background. And after participating in part 2 of the webcast series today, you decide you'd like to see part 1. That is available for viewing on demand on the WRF website. So today's webcast, part 2, is titled PdNA Pilot and Full-Scale Research and Future Directions. And today's webcast is going to focus on recent research on lab and full-scale PdNA research and emerging technologies, as well as include a discussion on future directions for PdNA research. So I'm going to go over a few housekeeping items as well as the agenda for today's webcast, and then I'll hand it off to our first speaker. So in terms of housekeeping, you can submit questions through the question box at any time. We'll do a Q&A at the end of the presentation, so just keep your questions coming throughout the webcast. Slides and a recording of the webcast will be available at www.waterrf.org. And you can download the slides now and access a link to the project page under the event resources on the bottom left of your screen. So those resources are available to you now. A certificate of completion will be automatically generated after the webcast. So if you have any questions about that, you can contact Michelle Suazo at the email shown there. And then we encourage you to stay on till the end to fill out a quick survey with your feedback on the webcast. So here's a look at today's agenda. I'll lead off with a brief introduction of the project, the WRF research project that is the focus and basis of this webcast today, and that's Project 5095, which is focused on mainstream deammonification, which is a shortcut nitrogen removal process. After I provide that introduction, we'll have 2 featured speakers today. Each speaker will have about 25 minutes. First up will be Dr. George Wells from Northwestern University, and he's going to discuss lab scale research and emerging PdNA technologies. In particular, can biological phosphorus removal be integrated with partial denitrification anammox? And George will be followed by Dr. Kartik Chandran of Columbia University, who's going to discuss partial denitration anammox processes, and greenhouse gas emissions and microbial ecology. After the presentations, we'll have about 25 to 30 minutes for a Q&A panel session, as well as a discussion about the future of PdNA research. And that panel session will include myself, along with Dr. Kartik Chandran, Dr. George Wells, and Dr. Heidi DeClipier from DC Water will also join us for the panel session. Unfortunately, Dr. Ramona Rafat at George Washington University had an emergency come up at work today, and she'll be unable to join for the panel session. So here's a look at today's presenters. In addition to myself, I'll be joined by Dr. George Wells, Associate Professor at Northwestern University, as well as Dr. Kartik Chandran, Professor at Columbia University. And on this slide and the slide that follows, you can also see everyone's contact information if you'd like to follow up with any of our speakers today. Both George and Kartik are co-PIs on the Project 5095 that I mentioned. And then joining us for the panel session at the end is Dr. Heidi DeClipier, Director of Clean Water Quality and Technology at DC Water, and also a co-PI on the WRF project 5095. That's the focus of today's webcast. And as I mentioned, Dr. Rafat, unfortunately, will be unable to join us for the panel session. So I'd like to provide just a brief introduction about WRF Project 5095. That's the basis of today's webcast. And the title for that project, 5095, is Mainstream Deammonification with Biological Phosphorus Removal. And I think, as many of you are acutely aware, utilities across the country are facing increasingly stringent nutrient regulations. And traditionally, utilities have employed, energy-intensive nutrient removal methods that often require costly external carbon sources, as well as operational expenses. However, PdNA, in particular with biological phosphorus removal, has the potential to achieve low effluent nutrient concentrations, but at the same time provides for reductions in energy as well as chemicals, including external carbon, as well as reducing the treatment footprint. So the overall goal of this project is to develop a proof of principle for different PdNA configurations with the integration of BioP removal, and to help move PdNA into full-scale applications. So ultimately, the implementation of this process can really provide utilities an effective way to achieve low nutrient limits, but at the same time reducing their costs. Here's a look at the project team for Project 5095. I guess we have 4 of our 6 principal investigators are on the webcast today. And unfortunately, I mentioned Rumana Rafat will be unable to join. Stephanie Klaus, the other principal investigator, was on part 1, was a presenter on part 1 of the webcast series. The project team includes 2 utilities, DC Water and Hampton Roads Sanitation District, that have conducted demonstrations at full scale and analysis of the methods. And then it includes 3 universities, George Washington University, Northwestern University, as well as Columbia University, that have conducted lab scale testing and analyses. And then the team also has 2 consultant firms on it, Black & Veatch, as well as Brown and Caldwell. The project team also had, or I should say the project also had a project advisory committee, or PAC, as well as a utility advisory committee. You can see the names of those folks there. The PAC provided technical review to the project, whereas the utility advisory committee was comprised of 8 utilities, relatively geographically diverse group of utilities that provided end user feedback and input for our research team. And just want to thank and acknowledge our PAC and utility advisory committee members that were part of this project. And then lastly, just a quick project status snapshot. I would like to note that this project was an EPA grant-funded research project. The project started back on September 1st, 2020, and just recently ended this year, April 22nd, 2025. The project had a total budget of about $1 million, and the primary deliverable from the project was this practitioner's blueprint or guidance document. And this really is intended to help utilities get a deeper understanding of PdNA, and in particular, how to implement PdNA at full scale based on the demonstrations that were conducted by DC Water and HRSD under this project. You can download this final report if you go to the Event Resources tab on your screen. There's a link to the project page where you can download this report. You might need to create a WRF user account to download the report if you don't have one already. But the report is free and publicly available. WRF published an initial version of the report back in October of 2023, and then we just published an updated version of the report in March of 2025. That updated version includes new information on integrated BioP removal with PdNA, as well as information on the nitrous oxide footprint of these novel DNR processes, both of which we'll discuss on our webcast today. So without further ado, I'd like to invite Dr. George Wells to present to start off, kick us off.
Thanks, Jeff. Really great to be here and have this opportunity to take part in this important conversation around partial denitrification anammox. I'm going to highlight some of the lab scale work that we've been doing over the last several years, really trying to dig into this question: can biological phosphorus removal be integrated with partial denitrification anammox? Right off the bat, I want to recognize a PhD student in my group, Zhen Jia, newly minted Dr. Zhen Jia, actually, just defended about a month ago. And most of the work that I'm going to be showing you today is part of his PhD thesis. Just a bit of a recap or overview from webinar 1. Key point I want to make here is that mainstream partial nitrotation anammox, or PdNA, is a very promising process, particularly for side stream treatment. In this process, we select for partial nitritation, conversion of ammonia to nitrite. It's a key step in provisioning nitrite for anammox metabolism. Mainstream application of PdNA has been intensively studied for 10 plus years, probably more than 15 years at this point. And there have been some major successes at lab scale, but robust full-scale implementation has not yet been achieved. Why is this? What is the key holdup? The key holdup is the fact that this entire process of PdNA relies on NOB outcompetition of those nitrite oxidizing bacteria, and that remains a vexing challenge at full scale. The types of controls that we implement at lab or even pilot scale are not readily amenable. They're relatively complex, and they're not readily amenable or translatable to full scale application. Fortunately, we have a couple of different alternatives for shortcut nitrogen removal, including not just PdNA, but also partial denitrification anammox. The key difference between PdNA and PdNA is the source of nitrite for anammox metabolism. PdNA relies on the NOB out selection route. PdNA rather relies on complete nitrification. So we want about half of the ammonia converted to nitrate. We basically give up on that idea, at least for now, of NOB out selection. And then we select for just partial reduction of that nitrate to nitrites. And then in an ideal case, that is handed off to anammox bacteria. And it turns out the controls for that PDN route tend to be relatively simple, surprisingly simple, actually. Also, the operational benefits of PDN are almost equal to, approximately the same as PdNA compared to conventional nitrification denitrification. At least theoretically, we can achieve aeration savings of about 50% and carbon savings of up to 80%. I do want to make the point that we typically talk about PdNA and PdNA as separate processes, but they're not really mutually exclusive. They can and often do exist in the same process. Most of my talk and most of our discussion today is going to be about PdNA. I am going to talk about a little bit of previous work that laid the groundwork for this work that focuses on PdNA. Mainstream PdNA for secondary nitrogen removal integrated into a secondary treatment process or for tertiary polishing has now been demonstrated at full scale. This is the focus of the webinar 1 in this series on May 13th, 2025. And I'd encourage you, if you haven't seen that, if you didn't take part in the webinar, very well worthwhile to go back and take a look. This is also the focus of much of our publication for WRF Project 5095, the final report of which is now published. Much less understood is how we take that PdNA and integrate it with biological phosphorus removal. And this is something that we've been interested in my group for quite some time. So just a little bit of a primer on biological phosphorus removal to make sure we're on the same page. EBPR, or enhanced biological phosphorus removal processes, rely on selection for a particular functional group called polyphosphate accumulating organisms, or PAOs. And selection for these PAOs requires cyclic redox conditions in a feast-famine feeding regime. So we start out with anaerobic conditions. This selects for hydrolysis of intracellular polyphosphate and release of phosphate into solution. This is coupled to uptake of carbon. Usually, at least in our conventional view of PAOs, this is fermentation products like acetate and propionate to replenish reserves of internally stored carbon, what's commonly termed ISC, internally stored carbon. Usually by this we refer to, or we mean, polyhydroxyalkanoates, or PHA. That's that purple circle within the POW here. And then in conventional EBPR processes, we follow this with an aerobic phase where we select for phosphorus uptake coupled to consumption of that PHA reserve and reduction of oxygen. There are many different flavors, of course, of EBPR processes, the simplest of which is just an AO process where we couple anaerobic and aerobic zones in a PFR type plug flow reactor type configuration. And what we would expect in this type of system then is under the anaerobic phase, what we want to see is release of phosphate, that's in red on the bottom here, and then the aerobic phase reuptake of that phosphate as polyphosphate. In parallel, in the anaerobic phase, we want to see a depletion of the soluble, the RBS-CoD. Here's the extracellular VFAs, uptake of those VFAs, and conversion to internally stored carbon. Usually that's in the form of this intracellular PHA in green here. And you can see that PHA is increased internally to the cells in the anaerobic phase, and then it drives that phosphorus uptake under aerobic conditions. There's a challenge though, because in conventional flow sheets, we often want to balance our goals of nitrogen and phosphorus removal. And we can certainly do that in many different creative configurations. These are quite common, of course. The key drawback is that these configurations in general require a fair bit of COD to drive those conflicting uses of COD. We have COD that's needed for denitrification, and separately, we need some form of BCOD that can be used for aerobic phosphorus uptake by POWs. In addition, these types of processes are generally energy intensive because we need to provide oxygen to drive both aerobic phosphorus uptake and separately to drive complete denitrification. So to address some of these deficiencies for a number of years in my group, we've been quite interested in a variant of POWs, so-called denitrifying POWs or DPOWs. These are POWs that are capable of phosphorus uptake, not just under aerobic conditions, but also coupled to nitrate or nitrite reduction. And these DPOWs are relatively poorly understood, but we think they offer a critical opportunity to couple nitrogen removal to phosphorus accumulation and recovery from wastewater. And we think there are a number of key advantages of DPAO-based bioprocesses. First, and this is really key, they use the same organic carbon pool to drive both nitrogen and phosphorus transformations. That PHA pool is used for both nitrogen and for phosphorus removal. And so this is at least has potential to be a very carbon efficient process. In addition, because we're moving away in a DPAO-based process from oxygen consumption, there are opportunities for energy savings. And most importantly for the webcast today, is an opportunity to think about partial denitrification or denitrification intermediates. In other words, nitrate reduction to nitrite, and asking the question, can that nitrite then be cross-fed with anammox? So the key research question is, can we combine that anoxic phosphorus uptake and PdN, partial denitrification, nitrate to nitrite, with nitrogen removal through anammox? And this efficient combination of shortcut nitrogen removal and biological phosphorus removal has been a focus of our work in combination or in collaboration with a range of different utilities and engineering firms for quite a long time. I'm going to take you back about 10 years to the startup of a shortcut biological nitrogen removal research station that we implemented at the O'Brien Water Reclamation Plant. This is in collaboration with the Metropolitan Water Reclamation District of Greater Chicago, where we evaluated a range of different strategies over about 5 or 6 years for mainstream shortcut nitrogen removal coupled to biological phosphorus removal. And I just want to highlight some of the successes and challenges of this past work, laying the groundwork for our PdNA efforts at present. So in this past work, I'm just going to focus on one of the processes that we looked at. We wanted to ask, can we integrate PNA, that's the NOB out competition route, partial nitritation anammox, with BioP in the same system, really by selecting for a system that mimicked a conventional anaerobic zone for selection for POWs. Then we followed this with an aerated zone, is actually with intermittent aeration, and for PNA and phosphorus uptake. And we operated this in a number of different modes. I'm just going to talk about the mode where we operated it in IFAS phase. Now again, NOB out competition was a major goal of this work. And for that purpose, we used a combination of intermittent low DO aeration, so rapid switching between anoxic and aerated conditions, robust nitrite sink via anammox, and very tight SRT control to wash out NOB and retain AOB in the system. The key takeaway from this couple of year project is that the system actually worked remarkably well. We were able to select for significant increase in anammox activity and abundance in the system over time. We were able to achieve quite high TIN removal, 91% or so, ortho-P removal, about 90%. We're able to route about 74% of the nitrogen through anammox. So this was a success in demonstrating that integration of PdNA with BioP, with combining biological phosphorus removal and anammox-based nitrogen removal. But there's a hitch, which is that in this particular process, that phosphorus removal was driven entirely by aerobic phosphorus uptake. The DPAO activity was very low. We really didn't see much phosphorus removal coupled to nitrate or nitrite reduction. And so we took this, this information, this study, and we decided, you know what, we really need to learn more from a fundamental standpoint about selection pressures and the like for DPAOs. And we went back to the drawing board and we identified a number of key challenges to DPAO-based anammox processes, in particular DPAO-based PdNA. The first of these was the need for new strategies, as I just mentioned, for selection for high-rate DPAO activity. The second is the need to develop understanding of capacity and drivers for DPAOs to only reduce nitrate to nitrite, so PDN by DPAOs. The third was to ask, can we integrate the activity of DPAOs with anammox via cross-feeding of nitrites? That really hadn't been investigated at the time. And the fourth question, which we're still kind of struggling with, is how do we control the competition for influent carbon between these desirable DPAOs and competitors, namely glycogen accumulating organisms? And of course, these questions, these challenges are the key basis for much of the work that we did as part of Work Project 5095. This is research objective 1 in that project, where we attempted to develop new PdNA concepts using denitrifying PAOs. We had two different tasks that drove our work. The first was to develop understanding of that PDN selection by DPAOs, and the second was to show proof of principle of PdNA with DPAOs as the main driver of nitrite production. I want to emphasize the work that we did was at lab scale, was relatively fundamental. We were specifically focused on the integration of DPAOs with anammox, and to enable identification of mechanisms and selection pressures, we wanted to simplify the system. So we actually didn't include nitrification in the system. We added a nitrification inhibitor. So we're only looking at that interaction between DPAOs and anammox in this particular system. Just a bit of detail about our experimental platform. I'm going to call this experimental platform 1.0, because at the very end of my talk, I'm going to tell you about our more recent implementation, 2.0. So this is just 1.0. We have a lab scale sequencing batch reactor operated in IFAST mode with anaerobic and extended anoxic phase, and then an aerobic polishing phase. There's a picture at the lower left of our 12-liter sequencing batch reactor. We dosed in some, or seeded with some EVPR biomass. Then we added some anammox-enriched biofilm carriers that we sourced from HRSD. And we operated this system in as a single SBR in IFAS mode. And the intention here was to see if we could select for DPAO activity in the suspended growth, and then cross-feeding of the produced nitrite. So selecting for partial denitrification, cross-feeding of that produced nitrite in green to anammox, which we intended to select for in the biofilm, on the K3 biofilm carriers in this case, in this particular system. So I'm going to show you a representative cycle from the towards the end of the operational period, let's say the good period of performance in the system. So typical SBR cycle, we have time on the x-axis. On the y-axis, we have about an hour anaerobic phase. And we dose in VFA, so our carbon source, beginning of the anaerobic phase. We have a anoxic phase. We dose in nitrate. Then we have a short aerobic polishing phase. So a lot going on here. So I want to draw your attention to the colored lines. Those are different nitrogenous species in blue, gray, and yellow. And then in orange here, we have phosphate. A couple of key things to point out. In yellow, in the anoxic phase, you can see a very rapid drawdown of nitrates. So we see very rapid denitrification, coupled in orange to a rapid drawdown of phosphorus. So we're seeing high rate denitrification and high rate anoxic phosphorus uptake. In addition, what we see is that a majority of that nitrate, the yellow, is converted to the blue line here, which is nitrite. We measure something we call the NTR, the nitrate to nitrite transformation ratio. That's our key metric for PdN efficiency. In this particular cycle, in this particular phase of operation, we're at a transformation efficiency of about 73%, I think, in this particular cycle, which is a reasonable NTR. So again, that indicates high efficiency partial denitrification. The final thing I want to point out is, where does that nitrite go to? It actually goes to a number of different sources, but one of the sinks for that nitrite is coupled to the gray line here. The gray line here with the gray X's, that is ammonia. And you can see that there's significant ammonia drawdown under anoxic conditions, and that's evidence of robust anammox activity and cross-feeding of nitrite to anammox. So how did we get to the state of relatively good performance? What we found, sweeping through a number of different scenarios and hypothesized selection pressures, is that an extended anoxic time with a nitrate residual and presence of anammox together selects for high DPAO activity coupled to robust PdN. Here we're just looking at a subset of operation here. Blue bars from light to dark blue indicate increasing initial nitrate concentration. That's a way for us in this lab scale system to control the amount of time when there's a nitrate residual in the system. So we're going from low to high nitrate availability. And you can see over this time period that we have an increase in the brown line here, that brown or orangish line. That's the NTR, the nitrate to nitrite transformation ratio. That goes from about 30% up to about 70%. That's our key indication of PdN efficiency. And coupled to this, we see an increase in the gray circles. The gray circles are the anoxic phosphorus removal efficiency. We get up to about 50 to 60% anoxic phosphorus removal efficiency, mainly through nitrate, which is what we want to see in this system. Coupled to this, what we also saw was a retention of robust anammox activity. When we dosed in anammox, we seeded with anammox-laden carriers. We initially saw a decline in activity and abundance of anammox, but then that leveled off, and it leveled off at an activity of about 0.09 to 0.1 kilograms nitrogen per meter cubed per day, which is actually reasonably good. It's actually higher than many of the published papers documenting attempts at mainstream anammox application. So we think what this shows us is that we indeed have demonstrated proof of principle of integrated DPAO activity with PdNA, exactly as we set out to do in this project. I do want to take a bit of a sidebar here and dig into mechanisms a little bit, because we were interested in where the PdN was occurring and how the suspended growth in this IFS system differed in function and in characteristics from the biofilm. There's a lot going on screen here. The main point I want to make is that the suspended solids were the main contributor based on different activity tests with different aggregates to both partial denitrification and to anoxic phosphorus uptake, as we had hypothesized, whereas the anammox were segregated really to the biofilm. But interestingly, we did find some phosphorus uptake, anoxic phosphorus uptake in the biofilm carriers. On the top here, this is suspended solids. The key thing I want to point out is that we saw an increase in suspended solids in the PdN efficiency. That's the black line here, the nitrate to nitrite transformation ratio, and anoxic phosphorus uptake rate via nitrate, which is what we want to see over time, which really suggests that the DPAOs in the suspended growth were adapted to nitrate-linked phosphorus uptake. That is what we want to see in DPAO PdN. We want them to consume nitrate and convert it to nitrite and then just stop there. What we found in the biofilm carrier was a bit surprising. What we found is that the contribution to phosphorus uptake was significant, but lower than in the suspended growth. We found that the NTR transformation efficiency was pretty low. It was almost non-existent. And in fact, the DPAOs that grew on the carrier in the biofilm were adapted to nitrite reduction. These, of course, are undesirable in this type of configuration where we want to select for PdN. So these results indicate niche differentiation for DPAOs via adaptation to nitrates, that's in suspended growth, and nitrite in biofilms, which we don't want to see. And in parallel, what we found is that that differentiation in DPAO phenotype was accompanied by a differentiation in the type of PAOs that we were selecting for. These are Acinetobacter PAOs, but strain level variation in those PAOs. In suspension, we selected for what we call clades 1A and 2F. That increased over time, and we selected for a completely different type of Acinetobacter in the biofilm, a clade 2A. So the key takeaway here is that these results suggest putative ecophysiological differentiation for denitrifying phosphorus uptake in Acinetobacter clades. From a process standpoint, this suggests that in a DPAO PDN system, we might want to aim for selection for these clades 1A and 2F. These may be specialists for nitrate reduction to nitrite coupled to anoxic phosphorus uptake. In my last couple of minutes, I want to switch gears a little bit. I've sort of profiled what Jen did in about 3 years of work. At the end of 3 years, we had achieved our project objectives. We had, I think, produced some interesting data, but we thought we could do better. And in particular, we thought that we could increase the anammox activity in this system. So we wanted to ask the question, can DPAO PDN rates and efficiency be improved if we move to a bit more of a realistic process flow sheet where we take those IFAS carriers and instead of having a single SBR, we move to a separation where the carriers are segregated to the anoxic zone. So we built another reactor and we implemented a suspended solids recirculation, really intended to simulate kind of a plug flow type system, where in the first reactor, we included only suspended growth. This is the anaerobic phase with COD feed. And in reactor 2, we have our IFAS system, those anammox-laden carriers, and anoxic phase with nitrate feed. To make a long story short, this particular change, this DPAO PdNA version 2.0, really boosted activity. We actually coupled this with a couple of other minor changes. We extended the anoxic phase, and we shortened the SRT to about 8 days. And together, this significantly improved ortho-P removal. On the upper right, you can see in purple, that's phosphorus removal efficiency or ortho-P removal efficiency that increased to nearly 100%. And most importantly, the TIN removal in yellow and the ammonia removal efficiency in red increased very significantly to close to 100% as well. What we found is that this was coupled to an increase in anoxic phosphorus removal rate, the DPAO activity, and that's the purple symbol on the upper left. That's phosphorus uptake linked to nitrate, denitrifying phosphorus uptake rates, and PDN efficiency in the lower left. You see in brown, that's NTR, that's our key metric for PDN efficiency. That increased to 80 to 90%, and our phosphorus removal proportion linked to nitrate. We don't want phosphorus removal linked to nitrite reduction. We want it linked to nitrate reduction. That increased from about 50 or so percent all the way up to 70 or even a little bit higher percent. We found also a very interesting shift in population structure where we found that this particular configuration seemed to really select well for DPAOs, for Acinetobacter. That's this top brown bar here, increase in abundance from 11 to 31%, and selected against our undesirable denitrifying GAOs. In this case, that's the orange Campylobacter here. So decreased to 16% of the population. And in parallel, we looked at stoichiometry and quantified dynamics in internal stored carbon, PHA and glycogen. And I won't go into details about this in this talk because of time, but the key takeaway is that we estimated that the contribution of DPAO to carbon turnover, to that storage of carbon, increased from 43 to 75%, and the contribution to denitrification of nitrate increased from 24 to 66%. And finally, of course, we wanted to select for high rate anammox. What happened? Were we able to do this? The answer is yes. Here you see a picture of our biofilm on our, in this case, K1 carriers. We see a pretty nice increase in biofilm thickness, the nice reddish color that is quite diagnostic for anammox. We see an increase in anammox abundance and activity. That's on the upper right here. And at the end of this operational period, the anammox activity at the reactor was about 0.23 kilograms nitrogen per meter cube per day, which is about a more than doubling from our previous configuration. We found that anammox contributed to about 70% of nitrogen removal. Last point I want to make from this DPAO PdNA 2.0 lab scale testing is that we found something a bit surprising, at least for me, which was that this new implementation had a significant impact on N2O generation. N2O is a very potent greenhouse gas. Of course, it is something that we don't want to see produced or certainly not emitted in BNR processes. So there's a lot of data on screen here. The key thing I want you to pay attention to is the blue line. The blue line shows the concentration of nitrous oxide. This is in liquid phase in our reactor going from day 21, right at startup. This is suspended solids only. Day 24 is right after we seeded with anammox-laden carriers. Lots of N2O production in both cases. Then we go to day 112, a couple of months later. We've selected for a very robust high-activity anammox biofilm, and you see that the production of nitrous oxide, generation of nitrous oxide, has decreased quite a bit. And we found that this is not just due to the presence of our biofilm carriers and anammox. Even when we look, this is on the far right-hand side, at just the suspended growth, which was very low in anammox activity, we saw very low production of N2O. And so we think that this mitigation of N2O production is likely due to both an increase in anammox activity, which provides a sink for nitrites, and likely a decrease in GAO abundance and activity. Denitrifying GAOs, in some cases, it's a little bit ambiguous in the literature, but there's some evidence that they are particularly prone to N2O production. So with that, I think I'm right at time, or even a minute or two over. So I'll zoom out of the weeds, come out of the weeds, and give you a couple of key takeaways. First, I think that lab scale testing has provided some quite promising evidence that integrated high rate, high efficiency DPAO PdNA is feasible in a couple of different configurations, but in particular, if we segregate carriers in an IFAS mode to an anoxic zone, which is what we would probably do in a pilot or full-scale system in any case, that really increases process rates and efficiency. The second key takeaway is really important, and that is if we think about what are the selection pressures that really lead to high DPAO PDN, or other types of ISC-driven PDN, the selection pressures that we identified are things like a high nitrate residual, or keeping a nitrate residual in the reactor, extended anoxic periods, keeping the rates of denitrification and of anoxic P uptake high, and maintaining a healthy reservoir of high-activity anammox biomass. And these are pretty similar mechanisms to what was highlighted in webinar 1. The schematic I'm showing you on screen is actually a schematic that was presented in webinar 1 for RBS COD, that is methanol, glycerol, or acetate-driven PDN. And so this suggests that the same similar simple controls that are applicable to soluble COD-driven PDN may be also applicable in some way to DPAO PDN or other ISC-driven PDN processes. The last point I'll make is that N2O generation is still an issue. I think it's still something that we need to look into, but we think that DPAO-driven PDN can be mitigated, the N2O generation, via selection for high-rate anammox, possibly by selection against DGAOs as well. So a very quick preview. We'll get more into this in the discussion. What's next? What are remaining research needs? There's a lot of exciting opportunities. The first is, I think, the need to move from these fundamental lab scale studies to more realistic process configurations for DPAO PdNA under realistic conditions, real wastewater, continuous flow with nitrification, and with other types of PAOs, for example, fermentative PAOs or other types of carbon sources. I also think there are ample opportunities for other variants of internally stored carbon-driven PdNA processes, not necessarily linked to, in all cases, to phosphorus removal. And finally, I do think that there are additional needs that need to be evaluated for mitigating N2O emissions. I want to point you to a couple of ongoing newer efforts that are looking at some but not all of these research needs. The first is WRF Project 5183. PI is Ahmed Al-Amari. This is really looking at detailed design guidelines for a variety of different types of PdNA full-scale applications. This does include, in part, an assessment in some of these configurations of internally stored carbon for PdNA. And then there's a newer DOE-funded project led by AECOM. The PI is Ganesh Raja Gopalan, evaluating, again, different types of configurations for technological upscaling of PdNA processes. And we're working a bit in both these projects. In the latter one, we're doing some work with DC Water to evaluate a couple of different possibilities in this area. So with that, I will wrap up, acknowledge the WRF 5095 team and my team at Northwestern, and I will pass the floor over to Professor Kartik Chandran.
Okay, thank you, George. I hope my audio is okay so far. Okay, so yeah, let me just pick up from where George left off. So it's a nice kind of sequence here. So I'll focus almost exclusively on field scale measurements, ranging from full scale to pilot scale, but all entirely in the field. And before I do so, I'd like to acknowledge, of course, the students and researchers in my group at Columbia who generated all this data, but also the immense contributions and collaborations from all the utilities where we performed this work. And so there are two directions that I'd like to focus on today, and these are somewhat related. The first direction is, of course, as George alluded to just now, it fills some of the information gaps relating to the production and emission of nitrous oxide from some of these technologies that are coming up and becoming more established. And then the second direction will focus on more of the molecular aspects, the molecular microbial aspects of achieving partial denitrification alone, just by itself, but with a focus on methanol-based partial denitrification. And so just to kind of complement what George presented today and what was presented during the last webinar, PDN, partial denitrification, potentially coupled with anaerobic ammonia oxidation, anammox, fulfills a very specific role in our quest towards resource-efficient biological nutrient removal as well, especially as we've seen the link between nitrogen and phosphorus. And we won't focus on each and every row and column here, right? At least maybe we can focus on this one set of reactions. And there are many ways to describe or quantify the efficiencies. On this slide, I just focused on quantifying the resource inputs in terms of electrons. So for instance, when we talk about full nitrification, ammonia to nitrate, we're talking about 8 electrons, nitrogen donating 8 electrons. And then when we talk about full denitrification, we refer to nitrogen donating or accepting, 5 electrons, going from nitrate down to nitrogen gas. And so if we consider that these electrons need to be provided, electron equivalents need to be provided, that's where I come up with this base case. And then comparing this base case to, let's say, partial nitration anammox, we are talking about a relative savings of about 77% based in terms of electrons, based on electrons. And then for PdNA, we're talking about savings of 62%. And so even though PdNA may not offer as high savings as, let's say, PNA, operationally, PdNA is a lot more tractable than or amenable to flexibility, versatility compared to PNA. And that's really where the attraction of PdNA lies, especially when applicable to mainstream nitrogen and or phosphorus removal. And that's really one of the key highlights that I'd like to to add in addition to what George has already presented today. And so the first aspect, let's get right into it. So the first aspect here is that of production and emission of nitrous oxide from some of these emerging DNR processes. I'm going to focus not just on those processes that include PdNA or integrate or incorporate PdNA, but also some of these processes where PdNA could be very well integrated. And just as a reference, I do have a PN-based side stream process as well. So let me just skip through some of these animations. So let's start with what we have as a reference. And this left-hand table is, I know that you cannot see my mouse, but on the left-hand panel here is the table obtained from the most recent EPA report, the US EPA greenhouse gas sources and sinks inventory for the United States 2024. And if we just focus on the row that is shaded here, N2O, we have data, all these numbers are in terms of CO2 equivalents. So nitrous oxide and methane have been translated into carbon dioxide equivalents. I just have these callouts here. So the number right at the very end, 2022, for nitrous oxide from wastewater treatment is equivalent to about 5 million passenger cars in the US, and that's not a very high number, but it's also not insignificant. Just to kind of also highlight, not too long ago, in the overall scheme of things, about 15 years ago, almost all the nitrous oxide produced in wastewater treatment plants was ascribed just to denitrification and just to the non-aerated anoxic zones. And we've since shown the first project that my group embarked upon was around 2007, also supported initially by the Water Environment Research Foundation at the time. And then as part of that project, we had developed a protocol that we have since modified quite substantially. And that's the protocol that we followed as part of this project as well, but quite a bit modified, quite a bit improved. And that protocol is available through the WRF website or through WRF as well. And so that's the protocol that we used, and this protocol entails measurement, real-time measurement of nitrous oxide, but also could include nitric oxide, nitrogen dioxide as well. We use a standard flux chamber that has been EPA approved for VOC measurements, but also off-gas measurements. And then finally, the flux chambers are what we employ for open surface tanks, and we get fairly good spatial and temporal coverage of these open surface tanks. And then in those cases where the tanks are covered, we connect the analyzer directly to, let's say, the off-gas vent. And so that is the approach. And I will jump now, instead of jumping to the results, I just want to also kind of set the stage here for some high-level discussion on the pathways. When we talk about nitrous oxide production and emission from nitrogen cycling wastewater treatment, we must recognize that it's not just, it is okay for us to say that emissions are from aerated or non-aerated zones, but it's also good to be able to look a bit deeper and understand the processes through which nitrous oxide could be produced and ultimately emitted. So based on our research, going back again more than 15 years, actually, we have discovered new pathways from both nitrification and denitrification within autotrophic nitrifying bacteria, which could lead to the production of N2O. And that N2O then produced, let's say, in aerated zones, would be stripped out right then and there. Or if the production is happening through denitrification in anoxic zones, or even through other reactions in anoxic zones, that N2O could be stripped out even from the anoxic zones, or quite a bit more from the, let's say, the upstream or the downstream aerated zones as well. So needless to say, the production of nitrous oxide in BNR and non-BNR plants is quite involves many different interactions between different organisms. Okay, and I won't go into too much detail at this point. Perhaps we'll have time for discussion at the end. Okay, so now let me jump to the results. So in this table again, all the way to the right-hand side, we have IPCC emission factor, which is present in the 2019 report, and that report actually does include some of our old WRF values as well. Anyway, the net average of all of those different studies is what results in this IPCC emission factor. Essentially, what this revised emission factor suggests is that 1.6% of the influent total kildal nitrogen is being emitted as nitrous oxide. This is again an average of averages and many more averages, and that's what that number is. Now, if we focus on the rows that are labeled PdNA on the left-hand side, ABAC, and pilot scale, these are the systems that are mainstream systems, and I'm not identifying the different plants, but these are the systems that are closest to either PdNA or systems that were going into PdNA or even just going into PdNA. And if we take a look at the column now titled percent influent emitted as in 2O, at least the high-level takeaway is that for these systems where there is substantial amount of nitrogen removal and the systems are operating quite adequately at the very least, which is not reflected in this table, but I'm basing this on operations data, the emission fraction is quite low, and it's also quite a bit lower, much lower than what the IPCC uses to describe our industry. And so that's a good thing. But inherently also, please, I'd like to emphasize what I just said. What is inherent to these low emission fractions is that these plants, these reactors are also doing very well in terms of nitrogen removal. Again, just as a reminder, all of these numbers, even in this table and from our previous studies, these are all based on field scale measurements with real wastewater in full scale for the most part, and there is one pilot scale system here as well. But again, in a real plant, faced with real conditions. And then just to kind of bookend, literally bookend these numbers, we have the step feed BNR process, which could be modified to accept the PdNA the model, and there we see again the numbers are quite a bit lower than what the IPCC suggests. They are a bit higher, but again, ultimately, see from our perspective, yes, nitrous oxide emissions are important, but so is, and perhaps even more, performance is even more important. And the bottom line here is that plants and reactors that are removing nitrogen adequately and not creating too many nitrogenous hotspots spatially or temporally, these are the plants that not just create better water quality, but also minimize emissions. That's a message that we first identified and presented in 2009, 2010, and it's very good to see that message is quite a unified message, and it keeps repeating in a sense as well. The last row here is for a side stream process, but again, the emissions are quite a bit higher, but we should also understand that in many cases, the side stream process is not a standalone process. The side stream process is in most cases integrated with the mainstream process as well. So again, we are looking for resource efficiency as related to overall BNR for the overall facility. So there might be a little bit in terms of, there might be a few degrees of freedom that we have here in terms of optimizing the collective system or optimizing individually these systems as well. And the other bottom line is that we really cannot link the identity of a BNR or a non-BNR process with the magnitude of emissions. It's how we design any given process and how we operate any given process, and it's the operations and design that ultimately ultimately then govern process performance in terms of water quality, but also emissions as well. Okay, we went a few steps further. We subjected the data that we got to machine learning-based modeling and also other non-parametric modeling. And so here, what we see on the left-hand side is such non-parametric modeling for all the data that we obtained collectively from all the aerated zones, and on the right-hand side from all the non-aerated zones. And all we wanted to do here was to identify factors that correlate, correlation here, not causation, correlate with the magnitude of these arrows, which are labeled as N2O flux. And so on the left-hand profile, we do see close spatial correspondence of the arrow that is identified as N2O flux with arrows which are identified as ammonia and DO. So these are ammonia, nitrogen concentrations, and dissolved oxygen concentrations measured in close proximity to where the flux chamber might have been placed, let's say in the aerated zone. And so essentially what we are seeing here, that in the aerated zones, essentially what we are saying is that any factors that result in high ammonia concentrations, any factors concurrently potentially with high dissolved oxygen concentrations are those factors that also result in increased nitrous oxide fluxes. Let me just spend a few seconds here just talking about one of these two, and we can come back to this later again. See, in a well-designed, well-operated nitrifying reactor, just nitrifying reactor, we would like the ammonia concentrations to be as low as specified or designed. And so essentially what we are saying is, if a nitrifying reactor is doing well, adequately, let's say the ammonia concentrations are low, and so are nitrous oxide fluxes from these aerated reactors. So again, this link between process performance and nitrous oxide production and emission. So inherently, what I'm also saying is that there is a narrative around nitrous oxide as it applies to wastewater treatment far beyond the overall carbon footprinting narrative. That I would say, in my view, that a much stronger narrative is that adequate operation and design of BNR facilities is directly correlated with their process emissions, at least as it relates to nitrous oxide. And so let's go to the right-hand side of the screen. If you look at the section of the graph where we have nitrous oxide, the N2O flux arrow, again, what we are showing here is that higher N2O fluxes correlate positively with high dissolved oxygen concentrations and high nitrite concentrations. Let's consider this for a moment. In a well-designed denitrifying process, let's say under anoxic conditions, we would like the dissolved oxygen concentrations to be as low as possible, ideally 0 milligrams per liter. But essentially what we are saying is, as the dissolved oxygen concentrations in these zones is higher or non-zero, these are the conditions under which nitrous oxide concentrations of fluxes increases as well. And again, the narrative is the same. Suboptimal design and operations results in poor performance, but also higher emissions. So that narrative still holds, and I'm happy to report that this narrative is what we had proposed more than a decade ago, and that still seems to hold for these new data sets. We are gathering more data even as I speak, and so we are subjecting the data to such analysis almost on a continuous basis. Okay, so then at least for the first section, essentially the findings are we just need to make sure that as we develop new technologies, new processes, we are able to capture the overall footprint of these processes and potentially link the nitrous oxide footprint at the very least to process performance and process efficiency. It seems the fact that we are now able to use some stronger non-deterministic modeling approaches that could be beneficial. Now, the last statements I'm that I'm going to make on this slide relate to analysis that we have conducted, not just based on this data set, but also other data sets. Again, when we talk about engineering, operation, control, monitoring, and control, really the solids residence time is one of the principal design and control factors that we have that we can actually manipulate and change. So one of the primary strategies for minimizing not just N2, but also maximizing performance or optimizing performance is, again, going back to the basics. What is coming out from even the ML modeling approaches, all of which I've not shown you here, is that at the highest level, paying attention to SRT and through SRT, paying attention to dissolved oxygen could be a primary strategy. By doing so, we can control ammonia accumulation. Ideally, we would like to minimize ammonia accumulation in the aerated zones. And correspondingly, we would like to minimize nitrite concentrations in both the aerated and non-aerated zones. There's a very, very strong biochemical basis to each of these factors that I'm mentioning. So again, I'm just happy to convey to you that through just non-parametric modeling, we are coming back to factors such as SRT, DO, and the other nitrogenous concentrations, which have a very, very, very good foundation and grounding in first principles. And so we're not violating anything. We're not coming up with something that doesn't make biological and physical sense. Okay, so that's the first part of my presentation. The second part focuses on the impact of organic electron donors on PdN. So I'm not talking PdNA now, I'm just talking about PdN. This is the overall schematic of denitrification, sequential reduction of nitrate to nitrite, nitrite to nitric oxide, and nitrous oxide, which are gases, and then nitrous oxide to nitrogen gas, obviously. And so in some cases, and not all cases, the relative amounts of electrons in the waste stream are not adequate for us to remove all the nitrogen. So in many cases, in these cases rather, we do need to resort to the addition of electron donors. Typically, we resort to the addition of organic electron donors for the just from a cost perspective. Methanol is quite widely used just from a cost perspective, but then glycerol is also being increasingly employed. Now, the basic question that we're trying to address here is how can we optimize PdN? When I say optimize PdN, and there are some data here, how do we essentially maximize the conversion of nitrate, but then stop the conversion of nitrate almost exclusively at nitrite? So we at the end of the day, we want all the nitrate to be converted, but essentially to nitrite, and we want to arrest the reduction of that nitrogen at nitrite and not have it go any further. So this would be the ideal scenario. And then again, the focus here of this part of the presentation is on glycerol and methanol, just because of the range of facilities and the broad range of facilities in which they are used. And so I'll first focus on, let me just skip through this. So I'll first focus on glycerol-based denitrification, and this is again past work that we conducted. This is these are the only two slides I'm going to show you, which are based on lab scale data. Okay, so glycerol-based denitrification. So again, the objective was to convert all the nitrate to nitrite and stop it from going any further. I just want to point you to this one arrow here that seems to kind of jump over some of these sequential steps here. And so that is the conversion of nitrite to ammonia, and this is also referred to as assimilatory or dissimilatory reduction of nitrite. But the end product is not nitrogen gas; it is actually ammonia. Okay, so let's start with the glycerol, and I'll just take you through the results. And so on these graphs, what I'm showing you is as follows. So on the left-hand y-axis, we are describing the nitrogen speciation in terms of fractions, and that is the second of these two bars that we plot here. So, and the legend is on the bottom right, And so essentially what we want is that this purple colored sub-bar, which represents effluent nitrate, should be as low as possible, should be as small as possible, because we would like all the nitrate to be converted, but then almost exclusively to nitrite. So this light blue sub-bar, the height should be as much as possible, as high as possible, and then any residual gaseous nitrogen, this cream-colored sub-bar, should again be as close to zero as possible. That's under ideal conditions. And then these squares with the error bars represent what we had defined for that part of the study as nitrate conversion ratio based on electrons. So the maximum that this ratio can actually, the fraction can actually, percent that we can achieve is 60%. So again, we want those squares to be as close to the 60% mark, which is on the right-hand axis. And on the bottom, the x-axis essentially represents the ratio of the influent COD to nitrate. So we tested again at different COD to N ratios, and we had also tested SRT values, which is not captured here. So essentially what we found was that at influent COD to nitrate ratios of 3:1 to 4:1, these really represent the sweet spot in terms of the squares, the nitrate conversion ratio being as high as possible and as close to 60% as possible. But also, while simultaneously achieving the highest level of nitrate conversion. So this purple sub-bar in the two center bars, they are the lowest, as quite low compared to let's say the left-hand profile here. And then on the microbial aspects, so these are the left bars here, the left-hand side bars here. Again, what we actually found that in the systems that were achieving good PdN, again glycerol-fed PdN, there was already a very, very high degree of enrichment of tauera, which are represented by these brownish kind of sub-bars here. So again, this was early on, so the papers came out about 3 years ago. The research was done a bit earlier. There was an indication that even with glycerol, which is seemingly consumed by a broad variety of organisms in activated sludge systems, just feeding glycerol and imposing conditions that favor PdN results in a fairly narrow microbial community. And that was very interesting because, again, we know that glycerol-based denitrification is supported by a very broad diversity of organisms. But the moment we would like to achieve PdN, that microbial community shrinks quite a bit if there is an enrichment. Okay, and then the question was, what happens with methanol? With methanol, again, I'm invoking the results from another web study from quite a while ago. Essentially, to summarize a lot of work that we did at that point, the metabolism one containing compounds, any molecules contain just one carbon, for instance, methanol, methane, CO2, and so on, relative to anything else. So there's this wide gap that exists between the metabolism of C1 compounds and anything else in terms of organic carbon metabolism. And there are very, very few organisms or groups of organisms that can actually make the jump. And so based on our previous results, what we had shown that in activated sludge, methanol utilizing denitrifiers are very distinct from glycerol utilizing denitrifiers. There is really, even metabolically, and I can come back to this during the Q&A, organisms cannot make jump. And so there is some crosstalk between methanol and ethanol, but glycerol seem to be very different. So then real practical implication here is that it doesn't really matter that we've characterized, let's say, glycerol-based PdN here. If we want to really understand methanol-based PdN, we really have to go into the system. And here, we conducted the study in conjunction with researchers at Blue Plains, DC Water, and the system was an IFAS-based PdNA system. And so this is the overall schematic. The focus is here on this zone here, labeled cells 7 and 8, which contains both media and suspended biomass. And the objective here was to really open up this black box of methanol-fed PdNA. I'm just resisting using the term methanol-based PdNA, PdNA. I'm just calling this methanol-fed PdN, and the reasons I hope will come clear in just a few minutes. These are performance data that we have as well. I'll skip through the approach, but essentially what we did is that we conducted sequencing at the DNA level, at the mRNA level, and then employed advanced bioinformatics to put together a picture that I'm going to summarize for you. So let's start with the results here. On the x-axis, what I have here are essentially phases 1 and 2 represent 2 distinct time periods for which we have performance on the previous table that I did not focus on. And then we have cells 7 and 8, which are essentially different zones in that IFAS zone within the overall PdNA scheme. And then we have samples that we obtained in the biofilm, and then samples we obtained from the mixed liquor from the session. And so, and then based on whole genome sequencing, this is not single gene sequencing, it's sequencing everything of everyone in the sample at the DNA level. And and this is what we saw. So if we just focus on the columns which are labeled biofilm on the x-axis, the y-axis represents the relative abundance in terms of the DNA sequence abundance. And so what we see here is that, let me just skip forward one. And again, this is an overall PdNA process. So in results that we are not too surprised by, the bulk of the anammox organisms, which are represented in this blue color here, Brocaria, related to Brocaria, they were primarily present on the biofilm. Again, this makes complete sense because anammox organisms, typically for kinetics and thermodynamics based selection, they prefer, they are afforded protection by the media, and that's where we found them. So this is again, please recall these are pilot scale systems running in the field with under real conditions. So that was good to see. On the other hand, in these mixed liquor samples obtained at different time points, we found essentially the dominance of methylotrophic organisms that feed exclusively on methanol. And again, please recall that schematic where I presented to you methanol-based metabolism sits to one side, everything else sits to another side. So we inherently we are showing that there is a selection. The moment we start adding methanol, there is a selection for these methylotrophic organisms. And again, I know you can't see my mouse, but I did label some of these organisms in the text. So, but the bottom line is already there's a separation. Anammox reside on the biofilm. Methylotrophic organisms reside mostly on the in suspension, but there are some in biofilm as well. Okay, and then what we wanted to do is that we wanted to move beyond, far beyond just the identity and the abundance. We actually wanted to go in and see not just what they could potentially do, but what they are actually doing. So to do that, let me skip this one slide. Let me go to this slide now. So basically, what I'm presenting to you here is are some data, are some results in terms of the sequence information that we obtained. So what I'm going to focus on here are this heat map, which is presented in green. And so the green heat map essentially is the ratio of the blue heat map and the red heat map. There's a color coding here, so all the samples that we obtained from the biofilm are shown in yellow. The samples that we obtained from the mixed liquor are shown in brown. I'm going to just make a few statements here, and so we can come back to the slide if there is time, if there is interest. And remember, this reactor, the system is fed with methanol, and we are focusing on that one zone. And this is the reason why I did not use the term methylotrophic PDN, because essentially what we see in this system is, even though we are selecting for a very narrow community based on methylotrophic organisms that are very uniquely positioned to just use methanol on the carbon side, on the nitrogen side, everything is happening all at the same time, even though we are trying hard to control the system and arrest the reduction at nitrite. So this is what is happening. We have organisms which are present in the biofilm, for instance, labeled BF. And then we have organisms which consume methanol, but they catalyze all the steps. We have certain organisms that consume methanol that do PdN. This is who we want in there. We have organisms that just take N2O, which other organisms are producing, and they reduce that N2O to N2, again, based on methanol, using methanol. We have yet other organisms that produce N2O and just stop at N2O. They can be taking N2O from any of the upstream steps, but they stop at N2O, again, supported by methanol. And then finally, we also have organisms that take nitrite and go all the way to nitrogen gas. And so this really is what is actually happening in this reactor. And I'm saying this is what is happening because I'm not focusing my results just on DNA, just on abundance, on the who and the how many. This is actually happening down at the messenger RNA level. So this really allows us, from a process engineering perspective, to even identify the reactions that are happening. And then when done in a proper fashion, as we have done here, we can actually ascribe quantitative weights to then take this into modeling and then figure out how much nitrogen is weaving through which step and how much nitrogen is being channeled through, let's say, PdN, full denitrification, and so on and so forth. So there's a direct link between the results I'm showing you here in words, but the numbers are behind the heat map and they can be translated into modeling. So again, in terms of key findings here, even for methanol-fed nitrogen reduction, even though we want PdN, even though we want PdNA, essentially what happens in reality is that everyone is everywhere and they basically go take the nitrogen into different forms. Yeah, so methanotrophic organisms are quite versatile, and this versatility was quite, even we were surprised by just the fact that everything was happening on the nitrogen side. The reactor was still meeting performance, but everything else was going on as well. There was a very specific differentiation between what was happening in the biofilm and suspension, even in this reactor. This advanced bioinformatics approach, which is already quite mainstream, the genome-centric multiomics, allowed us to really open up the box. We showed division of labor, competition for nitrogen, competition for dumping the electrons. Just everything was possible, even when fed with this with methanol, which selects for a very narrow group of organisms. Yeah, and then I would say that it is possible to achieve PdN with methanol, and I'm saying this is possible because we have results we and other groups have results from full scale, but again, we are operating in gray zones. It's not black and white, as we have seen. All the different combinations of nitrogen steps are supported even with methanol. The one thing I would like to say here is that there does seem to be an impact or implication of ammonia, which has thus far been very, very rarely considered in the context of PdN. The ammonia dynamics need to be investigated. We have results, microbial results here, but which are supported by other studies which are underway right now. And that is what I have. I'm sorry if I went over time, but again, I'd like to thank the utilities, the sponsoring agencies, and all the researchers from across the board who are involved in this work. Thank you.
Thank you, Kartik. We really appreciate you sharing your research and information with us. And also thank you, George, for your presentation as well. Now we've got about just 10 or 15 minutes left for a Q&A panel, as well as a discussion of the future of PdNA. And I'd like to welcome Dr. Heidi DeClipier from DC Water to our panel discussion. Encourage all of our participants to continue to submit questions through the box on your screen. We've had a number of questions come in so far, but any questions that were spurred by the presentations or any questions that you might have on PdNA in general you're welcome to submit. I thought we wanted to make sure we have time for it. I wanted to start with a question about the future of PdNA, and then we'll go into some of our participant questions that have come in. And this is for really all three of our panel members. where do you see the future of PdNA going in the next 5 to 10 years? In particular on the research side, what knowledge gaps do you see or feel that need to be addressed? And then, on the practitioner side, will more utilities adopt this technology, and what's needed to help facilitate broader adoption by utilities? So I'll put that out there, and feel free to jump in.
I can go first. So I can speak on the practitioner side of things. I think these are exciting times as we get more and more of these demonstration scale testing applications going in. So I think what we're going to see in the coming years is really more design guidance and really solving some of the design questions. I think we're going to see a variety of ways that we can implement it and a variety of ways of benefits that could be created in existing infrastructure. I think the coming years of focus is going to be a lot of retrofitting and trying to fit these technologies into existing plants for different reasons. A lot of it will be driven by capacity enhancements as well as potentially operational cost savings. So I think I'm really excited to see what these applications will bring and really solve some of these design questions so that we can really design it more aggressively and gain some experience of operation, right? Operational experience will give us more answers now in real life, what we might need to work on in the future.
Thanks, Heidi. George or Kartik?
Yeah, I can chime in. I definitely agree with Heidi. We're in a really exciting period of, at least in some aspects of PdNA, we're really in the engineering design phase and try to parse out different design guidelines, much less on the fundamental side, which is really nice to see that. For IS, internally stored carbon-driven PdNA, including DPAO PdNA, I think there's still a little ways to go, but we're at the point where that transition to realistic testing under, real wastewater, more complex conditions, dynamic conditions, realistic process flow sheets, and the like. That's really what we're primed to jump into at this point. I think we're beginning to do that a little bit in some of these newer projects as well. From a fundamental standpoint, I think I'm excited about some more mechanistic questions, trying to nail down exact mechanisms and controls, mitigation strategies for N2O. Kartik showed some really fantastic work in that space, showing pretty low N2O emissions in many cases. For ISC-driven processes, I think there's maybe a little bit more work to be done to understand how to control and mitigate those and drivers, and then trying to understand from a bit more fundamental standpoint, how sort of non-canonical polyphosphate accumulating organisms or PHA accumulating organisms can play a role in some of these processes as well.
If I can quickly add, this is a very exciting direction overall, which we refer to as PdN and PdNA. I'm not really sure that the microorganisms really care. So that's what excites me. Perhaps what we have been referring to as PdN, just PdN, right? Perhaps what we have been referring to as PdN is brought about by other dynamics of other nitrogen species as well. And perhaps if you can go in, first of all, from a fundamental perspective to understand what is actually driving, there are some insights especially based on the molecular data I showed. I think that'll allow us to kind of maybe parse through the noise and then zoom into, let's say, operational from a practical perspective, operational conditions. And then even decide whether PdN is where PdN fits and where it does not fit.
Thank you. Okay. All right. We're getting lots of questions coming in. We had a question come in. I think this one's for George. So if the nitrite clades are associated with the biocarriers, does that mean we really don't want biocarriers?
Yeah, that's a really good question. The answer is, I think, no, we do want the biocarriers. We need the carriers because for anammox retention, I think one of the things we've learned is that some form of biofilm process, I suppose we could think about some other substratum for biofilm growth. The carriers works pretty well for that anammox growth and retention. What I think we do need to do, though, is to protect those carriers to try to limit heterotrophic growth. DPAO, DGAO, and other heterotrophic growth on the carriers, try to push that into suspension. And I guess I didn't go into detail about this, didn't show data about this in my talk, but if you, in that version 2.0, generation 2.0 of the lab scale testing, where we segregated the carriers to the anoxic phase, no SCOD loading to the anoxic phase. It was just the anaerobic phase. We really saw that pattern of pushing the DPAOs and DGAOs and heterotrophs to the suspension. And at that point, in suspension, we really select for it appears those nitrate adapted DPAOs. So we need those carriers, but we need them in a particular place. I think that's the key lesson.
Right, very good. We had another question come in. I think this one's for George, but Kartik and Heidi, feel free to chime in. What is the role of SRT in selection for DPAO, PDN, and how essential are the ANA-AOBs as competitors for nitrite for such selection?
Yeah, that's a really, really important question. I think the data that we have suggests that the presence of anammox is pretty essential for moving to relatively high efficiency PDN. Without anammox, we were able to achieve 30 to 40% NTR, that nitrate to nitrite transformation ratio. With anammox, with a robust nitrite sink, we got up to 70 to 80% or so. So it seemed to really help. The question of SRT is really interesting, and I don't know that we have a full handle on that. We did sweep through SRTs in our work of between 10 and 18 days without anammox present, and we didn't see a clear pattern of influence on DPAO PDN. But we did see, this is interesting, that selection on the biofilm, which is long SRT for nitrite adapted PDNs, and a suspended growth where you, of course, have presumably shorter SRTs, the nitrate adapted DPAO. So that suggests that probably is a control. We're not, I would say, I don't know that we have that exactly nailed down what that SRT should be.
Thank you. I think we have time for maybe just one or two more questions, and then we'll wrap up. This one in for, I believe, Kartik. Would there be any N2O emission for partial denitrification from nitrate to nitrite? Is it possible to verify this through controlled lab testing?
Yes, yes, definitely. The quantification of the quantification of nitrous oxide production and emission from dedicated PdNA systems. I mean, we have relatively, we don't have as much data as we have on other well-established technologies and processes. So yes, we really need to go in and understand the emissions, but as a function of nitrogen and carbon dynamics as well. Part of this work can be done through isolated lab testing, but through some of the techniques available now, it may also be. I think we should do this in tandem with field testing, controlled as well. Yes, thank you.
Okay, thank you. Next question here. This one for George. Did you look at other denitrifiers abundance? And have you seen a correlation between DPAO's relative abundance compared to other denitrifiers and PDN efficiency or N contribution via anammox?
Yeah, that's a good question. We didn't look directly at denitrifier abundance. The data that I showed was mostly We had a little bit of qPCR for anammox functional genes, but mostly 16S RNA gene sequencing, which is a really common way of asking who's present in a community, but it's not as straightforward to identify from that data what are denitrifiers and what are not. I would hypothesize that most of the community members are denitrifiers, but we haven't really evaluated that yet. I will say that we have some shotgun metagenomic data from the same system that we're parsing through now, and from that data, we should be able to get at least a partial answer to that question. So maybe stay tuned. I can get back to, I think it was Ahmed that asked that question.
Great. Well, I think we're about out of time here. We got lots of questions and more than we have time for today, but anybody that asked a question, I want to let you know we will follow up with you in writing after the webcast to answer your questions. So don't worry, we will definitely get back to you and we appreciate your time in submitting those questions. So just want to acknowledge again that this project was funded under an EPA award to the Water Research Foundation, and thank EPA for that. And I want to thank all of you, our participants, for joining us today. And special thanks to our speakers today, Kartik and George, as well as Heidi, for joining the panel discussion. And since this also concludes our two-part webcast series, I want to thank our speakers in part one, Stephanie Klaus of the Hampton Roads Sanitation District, Krista Barbadillo, and Mike Parsons. Both parts 1 and 2 of the webcast series will be available for viewing on demand from the WRF website in case you missed any or would like to rewatch any of this. But thank you all for joining us, and I wish you a great rest of your day.